Okay, so capacitor is basically a charge storage unit. Charge builds up in the capacitor, and then we might be able to use it for another circuit, for another item, to do a certain job. It may be there to protect a circuit from over current. So like a surge protector might have a capacitor in it to pull extra current when, or pull extra charge when there's a surge on the line. So let's look at some capacitors. Here's the simulation. There's a battery, looks like a Duracell. These are two parallel plates. Okay, so parallel plates will store the charge. There's no connection between these two plates. But I'm going to take the battery, and if I turn up the voltage, now, do you see the blue arrows that show up just briefly and then kind of fade away? They only show up while there's charge moving. So when we open up the gates or increase the voltage, truly negative charges flow, because the electrons are the ones that move. The negative charges flow and start filling up this space. All right? Those negative charges repel the negative charges, or the electrons that would be in this metal plate, and they take off and go this way, leaving behind positive charges. So I've got little red positive charges up here, blue negative charges down here, and for every negative charge there's a positive charge. So what exists between two oppositely charged plates? Do you remember? How about an electric field? So they're stuck in the electric field. So as I raise the voltage up, what's happening to the amount of charge on the plates? Do you see that we have a lot more charge? What happened to the field lines? Did it get more dense? Maybe stronger between the two plates? All right, if I lower the voltage, it becomes weaker and weaker to 0. And notice as I was lowering the voltage, the direction of the negative charge flow changes. I increase it, decrease it, they change. So that's not the direction of conventional current. That's the direction of electron flow. Conventional current is exactly the opposite. It's what would your positive test charge do? Conventional current. Okay, so let's see. This is the capacitor. It's like a warehouse. How could I change this warehouse so it could hold more charge? Any ideas? I can make it bigger. What if I make this area bigger? What's happening to my positive charges? Are there more on there? Looks like, what, 9? Is that more than 9? Yeah. So by increasing the area of the plate, I've got more capacity for the capacitor. Capacity, that's where it comes from. Okay, so think about adding on to a building or adding more seats to a stadium. We increase the capacity. Okay, so that means, we'll hop over here, that means that our capacitance should be directly related to the area, the cross-sectional, or the area of the plate. And this isn't the area of both plates, this is the area of a plate. Of one plate. So don't double it. Rookie mistake is to double it. So area of one plate. Okay. Alright, so let's go back, and I'm going to make this area normal again. Now I can change the separation distance. What if I put them closer together? What's happening to our positive charges on there? Increased. So let's think about this. Okay, positive charges and negative charges really like each other. They really want to be together. But negative charges and negative charges, they don't like each other. So as I decrease the distance between these two plates, it's like their desire to be closer to the opposite charge is greater than the repulsion with the equal charges. So they scoot really close together so that there's enough room for everybody to get in there and be attracted to those opposite charges. So it actually pulls, because of the electric force between the two, pulls more charge onto the plates. So by bringing the plates closer together, we can actually increase